Okay, sorry for the interruption. We're now back. So just to quickly recap what we've studied last week, we talked about the concept of forced response and natural response. And when we talked about forced response and natural response last week, we've mentioned that the forced response is result of the external input that we've applied to a system. For example, if you have a system, you give it an input and it will produce an output. And we said that the ratio of output to input is basically your transfer function. And we said that if we are to plot this transfer function, we'll end up with two different types of responses. Initially, at the beginning of the output appearing, we get what we call the natural response. And the natural response, we said that it depends on the internal dynamic of the system, the way that the circuit is structured, the type of components that you have, and the values of these components. And then we also call that the transient or the initial output. And then eventually, if your input, for example, was a sinusoid, your output will be a sinusoid, and we call this the forced response of the system. And we said that the forced response solely depends on the input value of the system. So these are things that we've discussed last week. We also said that the natural response is called the transient because it happens initially in a transient time frame. And the forced response is the steady state response or the static value of the output. So we call that the steady state. So we've discussed these last week. In addition, we said that if your input was a sinusoid, your output will be a sinusoid with a certain phase shift and a certain gain or amplitude. And we talked initially about linear systems, and we mentioned that linear system is a system where the frequency, the operation frequency, is the same for all components of the system. So if your input is at a frequency omega, your output will also be at the same frequency omega. However, if your input has the magnitude or amplitude, the highest peak is V1, the highest peak of your output will be V2. It will have different peaks. And the ratio V2 over V1 is basically your gain, your system gain. And then we said that the phase shift difference between the input and the output. So here the phase shift is what? It's 0 degrees. Here it's phi. So phi is the phase shift of this system. So this system has gain and has a phase shift. And this happens, or this is the same expectation for all systems to have a gain and to have a phase shift. And if the system is linear, then you expect them to all operate at the same frequency, and your gain will be the ratio of the output to the input, which is V2 over V1, and the phase shift will be the phase difference between the output and the input. So these are all concepts that we've discussed in the previous lectures. Now, there are things that we'd like to keep in mind that if the phase shift is positive, so if phi here was positive, that means that your output is leading your input, which means in comparison to the input sinusoidal starts at 0, you can assume that this is starting at a prior point. And if phi was negative, we assume that this is lagging the input, the output, which means that it will start at a later point in time, your output. So these are all things that we've already discussed. So this is just a recap of previous things. In today's lecture, we said that we're going to discuss the concept of a Laplace transform function and a frequency response function. So what is the difference between Laplace transform and frequency response? We've already discussed the concept of gain and phase, but we'll discuss them in more details with examples and how to plot them. So earlier we said that Laplace transform function or Laplace transfer function h of s is equal to the output Laplace transfer function divided by the input Laplace function. Frequency response is whenever we take this Laplace transfer function and simply replace s by its equivalent value j omega. Once you do that, you've converted your function from a Laplace transform or Laplace transfer function into a frequency response function. For example, if we have this Laplace transfer function, h of s is equal to 2 divided by s plus 3, we can easily convert the s into j omega and end up with the corresponding frequency response function. H of j omega is 2 divided by 2 divided by j omega plus 3. So all you have to do is just simply convert the s to j omega, and this will convert your function from a Laplace transfer function into a frequency response function. If your transfer is V2 of S over V1 of S, then your frequency response will be V2 of J omega divided by V1 of J omega. So all you have to do is simply just convert each and every S by J omega in order to get a frequency response function. And the gain, we said the gain is the ratio of the output to the input. The gain, now because you converted it to J omega, you end up with a complex number. So the gain is the magnitude of that complex number. And the phase shift will be phase shift of j omega of v1 of v2, sorry. Let me rewrite it here. So this h of j omega is equal to the phase shift of v2 of j omega minus phase shift of v1 of j omega. So you'll just subtract phase shifts to get the overall system phase. And to get the gain, all you have to do is just evaluate the gain of v2 of j omega divided by the gain of v1 of j omega. So I know I'm going a little bit faster, but once we go through the examples, I think it will be more clear for you. And as usual, please let me know if you have any question or concerns. So let's take this for an example. Let me make some space for it. Let's say that I have this. Let's take it from here. Let's say that I have this Laplace transform function. The same as this. Now let's say that I want to evaluate the gain and the phase shift. What are these two equal to? Step one would be to convert every s by j omega. So this is what we will do. We'll say that instead of h of s, we will have h of j omega. So instead of this s, we'll have j omega is equal to 2 divided by, instead of this s, we will have j omega plus 3. So step one is to convert from a Laplace transfer function to a frequency response function. If I want to find the gain, which is g, is equal to the magnitude of the complex number h of j omega, which is equal. Now, because this is a fraction, this will be equal to the magnitude of the numerator divided by the magnitude of the denominator. Magnitude of 2, or the absolute value of 2, is 2. Now let's look at the denominator. This here, the magnitude of j omega plus 3. So this is a complex number, and we know that the magnitude of a complex number is the square root of the real part squared plus the imaginary part squared. So it will be omega squared plus 3 squared. So this would be our gain over here. If I want to evaluate the phase, which is theta, so the phase phi or theta is equal to what? Phase 2 divided by phase j omega plus 3, which in complex number, if you have a fraction and you want to evaluate the phase, it will be the phase of 2 minus the phase of j omega plus 3. Remember that the phase of a complex number is tan inverse the imaginary over the real. But here the imaginary is 0, which means that the angle here is 0 for 2. And here it will be tan inverse the imaginary part, which is omega, divided by the real part, which is 3. Which means that the phase shift over here is equal to negative tan inverse omega over 3, which is exactly what we have here. So up till this point, are we clear? So we just learned how to convert from Laplace transfer to frequency response by replacing every s by j omega. And we've also experimented with how we can calculate the gain and the phase of this frequency response. Up till this point, do we have a question? Is it clear to everyone?
Yes, Miss Clear.
Okay. So let's have another example. Let's look at this circuit over here. And if you look at this circuit over here, we have, this is the exact same circuit we've practiced with in the previous lecture for Laplace transform. We have a series RLC circuit. The output is at the capacitor terminal, so the output is V2, and the input is V1. And you're given values for L, which is 1 Henry, for R, which is 3 ohms, for C, which is 0.5 farads. And the question is, can you determine the gain and the phase shift of this circuit as a function of omega? So if you're not given omega. And then after that, if V1 is 4 sine 3t, can we evaluate V2? So it's a two-part question. Let's start with the first part. We'll just make some space. I'm gonna copy this over here. And I'll just copy component values. So we have 1, 3, and 0.5. So this is 1, this is 3, this is 0.5 farads. Okay, so the question is, determine the gain and the phase shift as a function of omega. So the question is, what is the value of gain? What is the value of phase shift? You just rewrite it here. So step 1, you have to find the transfer function. We need to find h of s. And then we will get h of j omega, and then we're going to use it to evaluate the gain and phase shift. So step 1, let's find h of s. We already know that h of s is equal to, we're told that the output is V2, so it's V2 of s divided by the input, which is V1 of s. So that would be step 1. Step 2 is to evaluate this h of s, which is V2 over V1. So we're going to use voltage divider rule, which we established last week, that V2 over V1 of s is equal to ZC over Z total, where ZC is the impedance of the capacitor, and Z total is the total impedance. We already know that ZC is equal to 1 over SC. So these are things that we've already done last week. I'm just repeating them to avoid any confusion. If you have any question, feel free to stop me. And then Z total is basically the series combination ZR plus ZL plus ZC, which is equal to R plus SL plus 1 over SC, which can be combined in a common denominator SC, and then we'll have S squared LC plus SCR plus 1. So this is Z total. We'll take this ZC and this Z total and substitute them here. So we'll get V2 over V1 is equal to ZC, which is 1 over SC, which is got from this, divided by Z total, which we get from here, S squared LC plus SCR plus 1 all divided by SC. These two cancel each other out. So V2 over V1 is equal to 1 divided by S squared LC plus SCR plus 1. Last week we learned about standard form, so just to standardize it, I'm going to divide and multiply by LC. So we end up with H of S, which is equal to V2 over V1 of S, is equal to 1 over LC divided by S squared, because these two counter each other out, plus S R over L, because these two counter each other out, plus 1 over LC. So the first step is we have to get the Laplace transform function. Step 2 is substitute S is equal to J omega. Or before we go to there, before we substitute, let's first substitute the values of components. So we have R equals to 3, L equals to 1, C equals to 0.5. So let's write it here. H of S is equal to 1 over L times C, which is 1 times 0.5, divided by S squared plus S times R over L, which is 3 over 1, plus 1 over 1 times 0.5. So 1 over half is 2, divided by S squared plus 3S plus 2. This is our H of S, which we can rearrange the denominator just to make it. Now, the next step I'm doing just to simplify when I convert S to J omega. So what I would do next is I'll take this denominator, which is a quadratic expression, and factorize it. So it becomes H of S is equal to 2 divided by, and then we'll factorize the denominator. So we're looking at two numbers. When multiplied will give me 2, and when added will give me 3, which is 2 and 1. So S plus 1 times S plus 2. This step is just for simplification later. But if you choose to opt out of it, you will still end up with the same result. So now we've done with establishing H of S. From there, I'm going to replace every S by S equals J omega so that I can convert the Laplace transform function here into the frequency response H of J omega, which would be equal to which will be equal to 2 divided by J omega plus 1 times J omega plus 2. So it will be 2 divided by J omega plus 1 times J omega plus 2. So all we've done is every S here has been replaced by S is equal to J omega. And here we end up with what we call the frequency response of the circuit. So up till this point, are we clear with the frequency response? Any questions so far? Okay. So now let's look into what we need to evaluate. The main question was find the gain. And we know that the gain is equal to the magnitude of h of j omega, where h of j omega is a complex number. So it will be equal to, if h of j omega is 2 divided by j omega plus 1 times j omega plus 2, then the magnitude is the magnitude of 2 divided by the magnitude of the first complex number times the second complex number. And this is complex algebra. If you find any of this a little bit difficult or hard to follow, please go through the tutorial number 1, which is uploaded in Moodle. It will help you with complex algebra. So it will be 2 divided by, and we said the magnitude of a complex number is the square root of the real part squared plus the imaginary part squared. And then here we have another complex number, so we'll also calculate it as omega squared plus 2 squared. So this here, this is the gain as a function of omega. Next, so this is established. Now we need to find the phase. The phase phi is equal the angle of the complex number h of j omega, which is equal to the angle of the numerator minus the angle of the denominator, which is j omega plus 1 minus j omega plus 2. So now let's evaluate it. Phase of 2, the complex part is 0, which means that the angle is 0. Here we have a complex number with a phase of tan inverse imaginary over real minus tan inverse imaginary over real. So it is equal to minus tan inverse omega minus tan inverse omega over 2. And this is our phase of this circuit, which I believe we should be having over here. So this is the gain, and this is the phase. So this is how you evaluate the gain and phase shift of any given circuit. If you're given any circuit diagram and you're told find the gain and phase shift of the circuit, all you have to do is first evaluate h of s. So this is step 1. Step 2, get h of j omega, and you get that by replacing s equals j omega in this h of s. Step 3, the gain is the magnitude of h of j omega, and the phase is the angle of h of j omega. Step 3 and 4 are purely complex algebra that you have. Now there is a one last piece to the question, which is here. Given that V1 is 4 sine 3t, can we find V2 of t? So simply all you have to do is, if V1, let me write it, if the input V1 of t is equal to what? 4 sine 3t. 4 sine 3t. Can I get V2 of t? So step 1, from here, I know that omega is equal to 3, because this is a linear system, which means that the omega is the same, which means that the gain, this gain over here, is equal to 2 over square root 3 squared plus 2 squared times square root, sorry, the first one is 1 squared and the second is 2 squared. 3 squared plus 2 squared. So we can calculate the gain. And the phase would be equal to minus tan inverse 3 minus tan inverse 3 over 2. So we can actually calculate the gain and we can calculate the phase. And from that, we can say that V2 of t would be equal to the gain multiplied by V1 of t plus a phase shift. So V1 of t is what? 4 sine 3t. So the gain multiplied by 4 sine 3t plus the phase shift phi. Once I evaluate what is the gain and what is the phase shift for omega equals 3, which I've already evaluated here, I believe. So when omega is 3, the gain is 0.17 and the angle is minus 127. So all you have to do is just multiply 4 by gain, 3t plus the phase shift theta. Does that make sense? So up till this point, is it clear to everyone? Before we move to the next part? Any questions so far about evaluating gain and phase shift of a circuit? Okay, so now let us move on to the second part of today's class, which is the most important part, which is the Bode plot. Bode plot is a graphical way to view frequency response. So we can evaluate frequency response by equation, by finding h of j omega, by finding the gain as a function of omega, and the phase as a function of omega. But there is an alternative similarly too. Now, if you're talking in time, we can say that V2 is equal to 4 sine 3t. This is an equation. We can also plot it as 4 with an omega of 3. And we can say that this is V2 of t and this is the t-axis. Similarly, we can say that h of j omega is equal to something, or we can plot it by saying, well, I'm going to plot gain versus frequency, or I'm going to plot theta versus frequency. So we can express it either as a mathematical expression, a formula, or as a graphical representation. So the graphical representation will have the x-axis representing frequencies. Bode plots are possible to be plotted using something we call the straight line approximation. There are other ways to graphically represent frequency response. For example, there is the Nyquist plot and so on, but we are focused on Bode plot. So the first thing we need to understand about Bode plot is its axis. The Bode plot can plot either gain or phase. So when you plot gain, you will plot the gain in decibels, I will explain that in a moment, versus the frequency omega in radians per second. Your x-axis represents frequencies, your y-axis represents gain. Your x-axis is not linear, so it means it's not ordered as 1, 2, 3, 4, all the way up to infinity. It's a logarithmic scale, which means that it has decades. So from starting point to the first measure, this is ones. From here to the second unit, these are tens. From the second to the third, these are hundreds. So 200, 300, 400, and these are thousands. So 2000, 3000. And we call each of these a decade. So the first decade is ones, 1, 2, 3, 4, 5. The second decade is tens, 20, 30, 40. The third decade represents hundreds, so 200, 300, 400, 500, and onwards. So we call this a logarithmic scale for the x-axis. And this applies to both the gain and the phase plots. However, when it comes to the y-axis, the gain is linear. So you go 0, 10, 20, 30, and it's all linear. And the phase goes by degrees. So 0, 1, 2, 3, and again, it is linear. That's the first thing we need to understand about the scale of the Bode plot. And the reason why we keep the x-axis in a logarithmic scale, it's because we want to view a wide range of frequencies from 0 to to megahertz, for example, or to gigahertz. So we want to see a very wide range. So that's why we compress the scale into this logarithmic scale. Step 2, once we know the scale, is that how do we plot the bode plot? The way we plot it, we use what we call the linear approximation, which means we plot it approximately based on the frequency response. So the bode plot corresponds to the frequency response. And there are few rules that we have to follow, or a few steps. So I'm gonna use our example, which is this transfer function. And I'm gonna use this just to explain to you how we use bode plot, and then we'll go back to the rules because it's easier to explain by example. Otherwise, it will be just random rules. So whenever you want to plot a bode plot of the circuit, you want to start with the transfer function. You want to start with the Laplace transfer function, not with the frequency response. So we start with this transfer function. H of s is equal to this. I'm just gonna copy it here and just scale it a little bit. So this over here is my transfer function. H of s is equal to this value. What you will do, step 1, is ensure that the second term here in every linear term with s on it is 1. So instead of s plus 3, I want it to be s multiplied by a factor plus 1. So to do so, we do a very simple step. 2 is a constant. We'll leave it as is. We want to get rid of this 3, but we want to be maintaining the value of the expression. So what I will do is I will multiply by 3 and divide by 3. So it becomes 2 times 3 multiplied by s over 3 plus 3 over 3. And 3 over 3 is 1. So what we did is we maintained the value of the expression, but we made sure that the second term with s is 1. And then we'll move to the denominator. S plus 1 is already in form, so I'll keep it. Here we have a 2, so I want to get rid of that 2. So what I will do is multiply and divide by 2, which will give me that this second term is actually a 1. And then if I look at these terms, I'll notice that the 2 at the numerator counters the 2 in the denominator, and then the expression that we have left is h of s is equal to 3 times s over 3 plus 1 divided by s plus 1 times s over 2 plus. So this is the format that I want to work with. So whatever I have, any type of transform function that I have, whether it's first or second or third order, I want to rearrange it into this format. And then I have to do the second step. So the step 1 is to put it in this format so that the second term is always 1. Step 2 is to identify my components. So here I have a mathematical expression. In this mathematical expression, you can have 3 possible components. You can have constants, you can have zeros, and you can have poles. Remember we talked about zeros and poles earlier, and we said zeros are values of s that will make h of s equals to 0. Poles are values of s that will make the denominator 0 and therefore h of s an undefined value. Constants are constant number. So if I look at my function here, I can clearly see that we have a constant, which is 3. 3 is a constant expression. And then we have zeros. We do have values of s that will make the numerator 0, which is if s is equal to -3, this will be -3 over 3 plus 1, which is 0. So we have a 0 at 3. And the reason why I'm ignoring the negative sign is because I'm dealing with frequencies and there's no such thing as a negative frequency. And then if we look at poles, I have two different poles. I have at s equals -1, so at 1. And then I have another one, which is at, oh, that's too close to the red. Let's use the green for it, which is at 2. So if s is -2, this will become 0, or if s is -1, this will become 0. So step 1, to rewrite everything into the standard form. So this is step 1. Step 2 is to identify your components, whether you have constants, zeros, or poles. So now I've identified that I have one constant, 1 0, 2 poles. So up till this point, are we clear? Are we following? It's very important to understand both plot, and it will be assessed in your final exam. So there will be a question asking you to plot a both plot. So please follow with me, and if you have a question, now would be a very good time to ask. Is it clear so far? Any question up till this point? Okay. So step 2, we evaluated the constants, the zeros and the poles. Step 3 would be to plot them individually. So step 3 would be to take each of these components that make up your transfer function and plot it individually. So if I'm to plot individually, I'll start with the constant. And the way you plot a constant is that you will find 20 log the constant. So if I want to plot 3, I'm going to find what is 20 times log 3, and then I'm going to evaluate it. So let's just calculate 20 log 3, which is 9.54. So we'll say that somewhere, if this is 20, this is 10, it will be somewhere over here. So the constant is always plotted as a straight line. So this is 20, 20 log 3. So we've plotted the first. All constants are plotted the same. You plot the constant as a straight line with the amplitude of 20 log the value. So if it was 5, it will be 20 log 5. If it was 9, it will be 20 log 9, and so on. Step 2, we're going to plot the 0. So we have a 0 at 3. We call 3 the break frequency. We call this value the break frequency. So what I will do is I'm going to look at where is 3 in my scale. So this is 1, 2, 3. This is my break frequency. Prior to the break frequency for zeros, the gain will always be equal to 0, which means we have a straight line at 0. Between 1 and the break frequency of 0. So from here all the way up to here, I will have one straight line which is equal to 0. And then at the break frequency, something happens, which is you start to increase in gain and that increase or that increment in value is basically 20 decibels per decade. What does that mean? It means that at 3 we started at 0 decibels. This point over here actually represents 30, represents 10. Remember we said ones, tens, hundreds. So if you start at 0, at 30 you should be at 20 decibels. At 300, you should be at 40 decibels, and so on. So basically, the rate of change or the slope of this line is 20 decibels per decade. So this is 20 decibels per decade. So this is the second element plotted. Third element is your pole, and the pole starts at 1. Which is here. So if you look at 1, so what we will have is a constant line starting at 1. Prior to 1, everything is slightly more, and start at 1. Let's color match it to my pole. And this is dropping with a rate of negative 20 dp per decade. Prior to that, it is 0. And then we have, so prior to that, by the way, what would it be? It would be 0.1, 0.2, 0.3, all the way until we get to 1. So that is the prior values. And then we plot the final pole, same way. The break frequency here at 2, so this is 2. So we'll have a straight line sorry. With the same slope of 20 decibels per decade, but it will be dropping. And then prior to that, it will be also 0. Which is what we have over here. So this again will be dropping, so which means if you start at 2, at 20 here, at 20, you will have dropped by negative 20 decibels. So therefore, the rate of change is negative 20 decibel, which is the unit of the gain here per decade. So this is step 3. We've plotted each and every component, the constant, the 0, the poles that I have, the poles individually. Step 4 is to combine these plots. Now to combine these plots, it means I'm going to add all these 4 lines into a single final line. But before I do that, I need to identify points of change. So I'm just going to use a straight line. Let's make it black. Let's make it very thick compared to the others so it will be visible. Let's make it dotted. So we have a point of change at 1. We have a point of change at 2. We have a point of change at 3. And all of this is continuous. So what I would do is I'm going to combine all of these together. So if you look at it, at the beginning, the only contribution comes from the blue line. So if we add all of them until 0.1, the only contribution is coming from this blue line. And then At 1 radians per second, we have only this purple line contributing. So this appears, which means that now instead of being a straight constant line, we do have a slight 20 decibels per decade drop. And then at 2 radians per second, we have two contributions. We have the purple and the green line contributing to the overall gain, which means that it will drop, but it will have a further drop. So if the drop here is negative 20 decibels per decade, the drop between 2 and 3 would be negative 40 decibels per decade. And then at that point, we have all 4 of components contributing. We have the red line. After omega equals 3, we have the green line and the purple line. So we have positive 20 and negative 40 because we have 2 dropping lines and only 1 increasing lines, which means that the total rate of change will be now back to, at this point, back to negative 20 decibels per decade. So this is how we plot the Bode plot for gain. And this single black line represents the total gain Bode plot, which is similar to exactly what we have here. So here we have a single constant. So this line represents the constant. This line represents the 0 at 3. The green and blue line here represents the poles. And the black line, you'll notice it starts steady. It drops here by negative 20, and then here by negative 40, and then back here to negative 20 decibels per decade. And the black line represents the overall frequency response of the system. So this tells you that at frequencies below 1, the gain is steady, there is gain. And then between 1 and 3, the gain starts to drop. So if you increase the frequency between 1 and 3, your gain will drop. And then after 3, your gain drops significantly. So this tells you that this behaves something similar to that. It is significantly dropping, which means that basically at these frequency ranges, we have a stable gain. From this point onwards, our gain is dropping, so our system doesn't really produce a proper output. Does that make sense? So this is how we plot the Bode plot for gain. Now we can also see how the phase shift with respect to frequency changes. And to do that, we'll do the exact same series of steps, but we have slightly different rules for phase. So for gain, we said that we just identify the break frequency, and then if it's a 0, we increase. If it's a pole, we decrease, and that's it. But for frequency response, we do something slightly different, which is we first identify the constant, and we know that the angle of a constant is 0 if it's positive. And constant, its phase shift is 0, absolutely 0. There is no contribution, 0 degrees. Now, however, if you look at the 0 at 3, so the 0 at 3, what I'll do is I'm going to define 2 points, 2 separate points. I'm just going to assume that this is ones, these tens, and these hundreds, just for ease. So these will be 0.1. The scale, I'm just referring to the decade. So we have a 0 at 3, which is this point over here. What I will do is I'm going to look at 1 decade prior and 1 decade after, or in other words, I'm going to look at 0.3 and I'm going to look at 30. My break frequency is here, 3. So I looked at 3 over 10, 3 multiplied by 10. Prior to the break frequency, or prior to the break frequency over 3, the phase will be 0. There will be no phase shift. Between 0.3 and 30, however, I will have a constant increase of 45 degrees per decade, which means that at 3, the phase shift will be exactly 45. At 30, the phase shift will be exactly 90. And then from this point onwards, the phase shift will be a constant straight line. Let me just plot it as a line. So from this point onwards, the red one, we're going to plot it as a straight line. So this is my frequency response for the 0. For the poles, we'll follow similar approach, but instead of increasing a constant increase, it will be a decrease. So this is 1. I'm going to look at 0.1, and I'm going to look at 10. And then I'm going to say prior to 0.1, it will be 0. Between 0.1 and 10 is going to be a steady decrease. Just to make it easier to follow, we always assume that whatever is in the denominator is decreasing, whatever is in the numerator is increasing. And then we'll have here a straight line. And the exact same thing happens to the second pole, which happens at 2. So I'm going to look for 0.2, and I'm going to look for 20. Prior to 0.2, everything will be 0 phase shift. Between 0.2 and 20, I will have a constant drop between 0.2 and here should be 20. And then after that, it's going to be a straight, stable phase. So just to write it down, pardon me. So this will be minus 45 degrees per decade, and this will also be minus 45 degrees per decade. So now we have individual components plotted. Step 4, sorry, we've already established step 3 is to combine them, but when we combine them now, we will have slightly different points of change. So we have here at 0.1, we have a 0.2, we have a 0.3. These are the points where changes happen. And then again at here at 1, just increase the length. And then at 10, at 20, and at 30. So 0.1, 0.2, 0.3, and at 10, 20, and 30. These are points of change. So if I'm to plot it, prior to 0.1, we had 0 phase shift. Between 0.1 and 0.2, the only contribution came from the purple line with negative 45 degrees per decade. Between 0.2 and 0.3, we have purple and green, so both poles are contributing to the overall phase shift, which means we have a 90 degree per decade change. And then between 0.3 and 10, we have red, green, and blue all contribute, and purple, sorry, all contributing. So we have one increase, positive 45 degrees and negative 90 degrees, which means it will be negative 45 degrees. So if I'm to write it, here we have negative 45 degrees per decade. Here, it's negative 90 degrees per decade, and here it's back to negative 45 because now the red line or the zero has an increment. Right. Then between 10 and 20, I have only the red contribution, the zero, and one pole because the pole at 1, the purple line, has stopped changing. So we have positive 45 increment, negative 45 decrease, which leaves me with a stable flat line. And then after 20, between 20 and 30, the only contribution is coming from the red line. So we have here a positive 45 degrees per decade increment. And then once we reach 30, we are back to stable, which is what we have here. We have steady state, a decrease with 45, a decrease with 90, a decrease with 45, and then a stability. So that will be the overall phase, which means, in other words, that at frequencies lower than 0.1, we have stable zero phase shift. Between 0.1 to 30, we have a constant phase shift, or not constant, sorry, we have a continuously increasing negative degree phase shift. And then at 30, it stabilizes and we have a stable 90-degree phase shift. Does that make sense? So this is how we plot the Bode plot. I know that it might look complicated, but if we follow these 4 steps in order, it becomes easier to follow. Step 1, rearrange your transfer function so that the term added to S is 1. Step 2, identify your constants, your zeros, and your poles. Step 3, plot your gain and phase shift for each of these elements independently. And then finally, combine them all by combining point-to-point addition. We call this the linear approximation Bode plot, and these are the rules for it. There are a few exceptions which you can learn by practice, but in general, we have the rules here. So I'll just go back to the rules. So if we have a pole, it's plotted by, so this is for the phase, it's plotted by constant decrease. This is its gain. Its phase is a constant decrease, but we start from break frequency minus 10 until break frequency times 10, which is exactly what we did. If you have a zero and not a pole, you'll have a constant increase of 20 decibels per decade, or you'll start at break frequency over 10 until break frequency times 10, with a constant increase of 45 degrees per decade. So this is how we plot Bode plots. Up to this point, do I have a question? Any concern? Okay, so I'm going to add to you more examples so you'll find more problems to practice with in Moodle. But keep in mind that this is very important to understand, very important to practice with. It will be assessed in your final exam and it will be assessed in your group assignment.